Now we should be able to go live.
Yeah, we are live.
Okay, perfect. Hi, everyone who's joined the meeting. I'm Bhumika. I'm one of the co-organizers of PyLadies. And for those of you who are joining for the first time, we're PyLadies Amsterdam. Uh, we're an NGO that we're an NGO that aims to improve the gender ratio in technology by helping women upskill in Python. So we aim to have a higher ratio of women and people in the LGBT community and help teach them Python through live workshops, live events. So that's enough about us. I'm going to hand the floor over to our speakers, and they will have a workshop today about an introduction to geodata using Python.
All right, thank you very much. Hello, everyone. Good afternoon. So before we dive into the world of geodata and Python, I would like to start with this image. This is a breathtaking satellite image, I would say, right out of the coast of Florida. And yeah, in this image, you can see the impact of Hurricane Ian. So we see dark fresh water that is filled with dissolved organic matter that's flowing right into the Gulf of Mexico. But you can also see the blue aquamarine color around it. And this is actually also a result of the hurricane stirring up all the sediments that results in this color. So imagine the wealth of information that's actually encoded in this image. So you can see urban development on the right, but you also see a lot of environmental change in the center and the left. So today we'll start exploring how we can use Python, or how Python empowers us to unravel these types of stories hidden in these pixels. First of all, let me introduce ourselves. My name is Amber Mulder. I have a background in geomatics engineering, and currently I'm a software engineer at Planet at the soil water content team. And with my team, I'm responsible for developing and maintaining the so-called soil water content product. I've added a screenshot here of our product. So this is a measure of the amount of water in the top part of the soil, and we use satellite data to calculate this. And yeah, our data is used by a lot of different customers in different types of applications, such as agriculture, for instance. This data can be used to make informed decisions on irrigation strategies, but we also have customers who use it to protect farmers against drought via insurance policies. And these are just two examples of the cool things that you can do with this type of data that I help to create. And we have Margot.
Hi, I'm Margot Jurikov, and I recently joined Planet as a software engineer, and I first did my master's in Delft at Geoscience and Remote Sensing. And now I'm working in the crop biomass team. Here's an example of the kind of data we work with. So we aim to deliver daily map and time series to farmers to help them make informed decisions about using irrigation or predicting yield or detecting diseases in their field early on.
All right, thank you, Margot. So we both work at Planet, and just to tell you a little bit more about Planet, Planet is a leading provider of global daily satellite imagery, and we also provide other geospatial solutions. So the company is driven by the mission to image the whole world every day, and we would like to make change visible, accessible, and actionable. So our motto is use space to help life on Earth, as you can see right here. The company was founded in 2010 by 3 NASA scientists, and we operate the largest Earth observation fleet of imaging satellites in the world. So we have over 200 satellites in orbit right now, so that's quite a lot. And yeah, with these satellites, we can provide up-to-date views of the changing landscapes on the Earth. So our data can be used in a lot of different types of applications, such as in agriculture or environmental monitoring, disaster response, or urban planning, yeah, you name it. And yeah, we can help businesses, governments, researchers, and journalists understand the physical world around us and use our data to actually take action. So I think that's pretty cool. Yeah, but what will we do today? Today you will learn the basics of geospatial data theory. So we will cover raster, vector, and other related geospatial concepts. And you will be introduced to some Python libraries that you can use for working with geospatial data. And we will also directly gain some hands-on experience with working with some of those libraries through some notebook exercises and by using some planet satellite imagery as an example. So we've selected a case study for today. You can see an image in the background here. This is in Greece, right outside Alexandroupoli, which is a city, and I'm probably pronouncing it wrong, but I don't know how to pronounce it exactly. So according to the New York Times, in August alone, in 2023, more than 350 wildfires broke out in Greece. And yeah, on this satellite image, you can see the most severe one that is right outside Alexandroupoli. And these types of images can really help to come up with solutions for wildfires throughout different stages of wildfires, like emergency management response or recovery after the fire. And today we will work with imagery taken by our satellites before, during, and after this enormous wildfire has occurred. And our goal is to analyze the effect of the wildfire on our case study. And we will try to locate the forest patch area that is affected the most in our case study area. So to give you a bit more context or an overview, actually, this workshop will be divided in 3 parts. The first part will be about raster data. So we will see how we can handle satellite imagery, which is raster data, in Python. Then in the second part, we will use land use data, which is vector data. And we will try to locate the forest patches in our study area. And then in the last part, we will combine the different types of geodata, and then we will actually try to locate the forest area that is the most affected by the wildfire. Okay, but what is geospatial data exactly? Geodata is information that is tied to a specific location on Earth. So it's like data that has a GPS tag attached to it. So this data can really help us understand and interact with the world around us, but then in a digital way. So think about your smartphone app, for instance. You probably use it often to find a restaurant or to get directions or to see where your friends are. And it's actually using geodata for these tasks. So the app actually knows where you are on a specific map, where the restaurant is, and how to get there because it's using geodata. Geodata can come in various different types. So I've collected some examples here. For instance, GPS coordinates, weather data, and topographic maps. And my favorite, of course, satellite imagery, also an example of geodata. Yeah, so geodata is all about using the data to understand and work with our physical world. And it actually plays a major role in large aspects or parts of our daily lives, even if we don't really realize it. I would like to discuss one important concept related to geodata, and that's the coordinate reference system, also called the CRS. This can be a bit complex, but I try to keep it a bit short and simple. But it's important because what makes data geodata is that the data corresponds to an actual location on the Earth's surface. And a coordinate reference system is exactly what we need to do this. Unfortunately, it's not an easy task because of 2 reasons. The first reason is that, unfortunately, the shape of our Earth is not a perfect sphere. So it's actually rather shaped as an ellipsoid, but it's also not a perfect ellipsoid either. So it's very difficult to create a model of our Earth. The second problem is that the world is 3-dimensional, as you might know, 3D, and it's not 2D like the maps that we were trying to create. So to tackle the first problem, that was the irregular shape of our Earth, we can choose or create an ellipsoid, which we would also call a datum, that follows the Earth's surface at the location of our data the best. So for instance, you see this example here. Imagine this is 3D, but then the blue line represents the irregular surface of our Earth. And yeah, you can see it's quite complex. So we cannot really make a simple model for this, a simple 3D model. So what we do is we create ellipsoids. The two different options are the orange one and the red one over here. And let's say we're interested in North America, which is right there. Then you can see that the orange ellipsoid fits the surface of the Earth the best. So if you have a data of North America, you would choose the orange ellipsoid. But if you look at South America right here, then this blue line is quite far away from the orange line of the ellipsoid. So there, the red ellipsoid would be more suitable. And then we have the second problem. So that was that we now have this 3D model, the ellipsoid, but it's 3D and we want to have a flat map. So for that, we need a projection. And a projection offers a mathematical transformation to make the world flat. So you see some examples here because there are different options of how you would tackle this. And so together, this datum and this projection form the coordinate reference system. Okay, there are two main types of geodata. Yeah, each of these two types have their own distinct characteristics and applications. And today we will explore both of them with our case study. But yeah, you have raster data and vector data. And raster data is the one you see on the left here. And with raster data, the data is stored as a grid of regularly sized cells. So each cell in this grid has a value that tells us something about the Earth at that location, like how hot it is or what kind of land is located over there. And we call this an attribute. So each cell in a raster corresponds to an actual location on the Earth's surface. Satellite imagery is an example of raster data. And then the other one is vector data. You see it here on the right. With vector data, the data is represented in a symbolized way, so as points or lines or polygons. And rather than with raster data, the shape of each individual line or polygon or point can differ. And it's very useful for representing information that has really discrete boundaries, such as building footprints, for instance. And then again, you can have attributes, and these can be assigned to each individual feature, so to each individual point, each individual line or polygon. For the first part of this workshop, we will look into raster data, because let's go back to our case study. We have this satellite image of Greece, and yeah, we want to analyze and to identify the forest area that's affected the most by a wildfire. And our image is raster data, so that's what we will start working with. Before we dive into our first notebook, I want to tell you a little bit more about raster data. So yeah, as I mentioned before, and you can see it in the example here a bit more clearly, raster data is a type of geodata in which which geographic phenomena are represented by a grid of cells. And each cell on a raster data set has a specific value. So you can see these values for each pixel. And this is information about a certain attribute, such as elevation, land cover, rainfall, or temperature. Yeah, some example of common raster data sets are land cover maps. And then every color represents a different type of land cover. Digital elevation models are often stored as rasters. So then every pixel or every cell in this data set then shows the elevation of a specific area. And my favorite, soil water content data. So here, every pixel, for every pixel, the soil water content is provided. Yeah, so geospatial rasters are actually very similar to a digital photograph. The only thing that's different is that geospatial rasters comes with some spatial details that link this data to an actual location on the Earth. And one example of this type of details is the extent. And the extent describes the geographic area that the raster is covering. So it defines the outer edges, which are shown here. Yeah, or the boundaries, you could say, of the raster in the coordinate system it's using. And another important one is the resolution. So the resolution is the size of each, the size of the area that each pixel or each cell in the raster covers in real life. So 8-meter resolution would mean that every pixel represents an 8 by 8 meter area on the Earth's surface. And you can see in the example here that when you have less pixels to represent the same area, which we would call low resolution, the image looks quite blurry. If you have more pixels to represent a certain area, which we call high resolution, then the image looks a lot more clear. The really cool thing about raster data is that it can contain multiple bands in one data set. So a famous example is imagery, RGB imagery. And basic color images, they all contain 3 bands, red, green, and blue, which represent the intensity of light of that part of the electromagnetic spectrum. And if you combine these 3 bands, you get the images, or the basic color images that we all know. But all these bands, they all have the same CRS, coordinate reference system, same resolution, same extent. There are many different geospatial Python libraries that exist for working with raster data, and I've listed some of them here. There are also links to documentation here, so you can check that out later on. But for today, I would like to focus just on the first 2 only. GDAL is the library that allows for geodata translation and processing. And it's an important one because the majority of spatial software actually depend on GDAL. And what's also a fun fact is that the original developer of GDAL actually works at Planet. But my favorite is actually Rasterio, and that's the one that we will use today. This uses GDAL under the hood, but it's a lot easier to work with, in my opinion, because it uses more a Python-like language style. And Rasterio allows you to read and write raster files into NumPy arrays. And you're probably familiar with NumPy arrays, and that has a lot of advantages, which we will see later on. Okay, back to our case study.
We have a question. It's related to the libraries you just mentioned. Maybe we can take time for it now.
Of course, yeah.
It's on the chat, and it's somebody asks, Tani asks, so sorry about saying your name, but somebody asks for geodata, is Python the best tool to handle it, or is it currently the most used?
I think it's the most used tool at this moment. And to be honest, I have 99% of my experience is in Python, so I would not be able to compare to other libraries or to other languages, but I'm pretty sure that it's the most common language now that people use for working with geodata. Does that answer the question? Or,
I think so. Otherwise, please let us know if it answers the question or if you have more questions.
Okay, so back to the case study. So our job for today is to find the forest patch that is affected the most by the wildfire. And in order to be able to analyze this, we need to know how to work with raster data in Python. So let's dive into our first notebook. Let's see. Yep. So I hope you all managed to follow the installation instructions and to create the content environment. I will share my screen, as I'm already doing, showing the notebook, and you can follow along if you want on your own computers, or you can just watch the screen. Feel free to do whatever feels comfortable. So we have a solutions folder and a workshop folder. So I'm going to the workshop folder now, but in the solutions folder, we have the same notebooks, but then with the solutions, as you could have probably guessed. And in the workshop folder, we have 3 Jupyter notebooks, and now we will start with part 1. But we also have a data folder that contains the data that we're going to work with, and some images that are used in in some of the notebooks. So when you open the notebook, it's important to check or to make sure that you're using the content environment that you created. So for today, we are going to use the geodata in Python content environment. Yeah, the notebooks are quite full with text. I will not read this out loud right now, but this is there so that later on you can go back to the notebook and yeah, recheck again some parts that you're interested in and to get some extra information. But for now, we'll just focus on the cells, on the code. And yeah, our goal here is to use Rasterio and to see what we can do with Rasterio with raster data in Python. And for this part, we will look at a satellite image that is captured right during the wildfire. But first, we need to import the library, of course. And we're also going to import pathlib that will help the handling of the file paths for us. So I will do that. Then you can open a raster dataset very easily with the open function in Rasterio. So this is the path to our image. And you will have it also stored in the data folder. So you can just run it. And then it creates a dataset object. And this is this open function that Rasterio has is very similar to the built-in Python open function that you may know. So the object that you create also has very similar attributes, such as the name and the mode. It's now in reading mode. But also closed, and this is an important one. You see that it's now closed is false, so the data set is actually open, which means that we are currently using the associated memory resources. So it's always important to close your object, your data set once you're done with it to release, again, the associated memory resources. Rasterio has its own plotting functionality, and it uses matplotlib under the hood, but it's really nice because it's very easy to plot your data. So you just need to import it like this, and then you can feed it your opened raster data set, and then we see the image. So here we see the part of Greece, of our study area, and you can see actually that the fire is still there, or at least there's quite some smoke still there. And you see all these burned down parts as well. And the cool thing about the show functionality of Rasterio is that the coordinates are already automatically put on the axis. So it does not start at 0, for instance, and goes to cell width and cell height, but it immediately gives you the coordinates. Remember, it's an RGB image, so basic color image, which means that it actually consists of 3 bands, red, green, and blue. And you can also plot these bands individually. So we can again use the show functionality. And this is the data set. And then you can just provide the index of the band that you're interested in. And it's a bit annoying, but the index starts at 1 and not at 0 because it follows GDAL's conventions. But yeah, you can just use the show function to plot individual bands as well. And remember that together, if you put these 3 bands together, you just get this color image. The file that we are working with today is a geotiff file. This is a very famous georaster format. And the object that you created also has attributes that are part of this geotiff file. So for instance, the shape means that our file has 2,554 pixels in the width, and then the height, or the other way around, sorry. And then in the height, you have 3,864 pixels. You can extract this also by themselves. Then an important attribute is the count attribute. This returns 3 now, so that means that our data set has 3 bands, so red, green, and blue. You can also access the different data types. So it returns for every band what the data type is. And the coordinate reference system that we learned about before, it's stored as in an EPSG format, and that's quite a famous format for storing coordinate reference systems. I've added a link here to get more information on this specific coordinate reference system, but as you probably have guessed, this is a specific coordinate reference system that fits our part of the Earth really well, our part of Greece. And then the meta attributes, last attribute I would like to show. This is a nice one because it gives you a dictionary, and this dictionary is actually a summary of the most important metadata of your object, of your data set. Yeah, you recognize most of them. These last two are really important for the geo part. So I'm going to go into much detail now for transform, but I've added some exercises that you can do in your free time at the end of this notebook. But basically what you need to know is that the CRS and the transform together allow to map your data to an actual location on the Earth's surface. So working with imagery can be quite challenging because the files are usually quite large. So it's a lot of data that you need to work with, and you usually perform quite some complex operation on this type of data. So what's very useful about Rasterio is that it loads your data into NumPy arrays, and NumPy arrays are very efficient with storage, and they also have some easy way to do element-wise operations, and many other tools also use NumPy arrays as inputs. You can use the read function. So again, we have this data set, or the read method, sorry. And then you can read your data into a NumPy array. And now I'm printing the shape. And you can probably already guess what this means, but 3 is the number of bands. And then we have the height and the width again. If you print this array, you get a NumPy array just like you are probably familiar with. So 1, 2, 3 bands here. Raster data also comes with many bands, and as I already said, that's quite some data, and you are often not interested in all this data. So sometimes you are, for instance, only interested in the red band because you want to do a specific analysis on this red band. And Rasterio allows you to then read only the bands that you're interested in. So you can again use the index of this individual band, and then it's loaded in a NumPy array. But this time you see the 3 is gone because it's just a 2-dimensional array. And if we print it, we see the values right here. Okay, so in our image, we saw that at the top left part, there's quite some forest. I'll scroll back really quick right here. So we now have NumPy arrays. So it's really easy to extract one individual pixel. So let's say we want to extract a forest pixel right here, and we want to plot it to see its color. We can easily do that by just using the rows and columns of our NumPy array. So I already saw that at row and column 10 and 100, there's a forest pixel. So here I extract it from the NumPy array. I want all the bands, red, green, blue. And at this location, if I plot it, so now I'm just plotting this pixel, it's green. So that's nice. So now we will start with a first exercise for you guys. At this specific location, this row and this column, there will be a pixel full of smoke. And your task is to try to extract this pixel and to plot it, just like we did with the forest right here. So you can actually use the same approach as presented right here, but then now this time for a smoke pixel. And we'll give you, I think, a couple of minutes to go for it. And then in a few minutes, we will continue and I will show you the solution as well.
So we have a question in the chat that you can also maybe answer right now.
All right.
So as a rule of thumb, raster data is not continuous. So in this case, can the raster file that is loaded be transformed to a higher resolution, that is more cells than the value currently showed in dataset.shape?
Sorry, it was the opposite, that raster is continuous and vector is not.
Oh, I'm so sorry. Yeah.
So is the question if you can change the resolution of the raster dataset? Do you understand that correctly?
Mm-hmm. Yeah, so like the file that we just read in, when we outputted the shape and were given the dimensions, if it's continuous, is it possible to, magnify that resolution to have more cells?
You can. You need to use interpolation techniques for that, but you can interpolate the cells, and then I don't know if you're familiar with interpolation, but that allows you to kind of fill in the data that is not there at the moment. So you can use different tools for that as well, and especially GDAL, the first library that I mentioned, has some nice functionality for that.
Okay, cool. And is that like it can be very computationally expensive depending on the size of your raster?
Yeah, but if you add more pixels, so you want to, that's what you are trying to do, then the size of your file will increase because you have a lot more information that you're trying to store.
Okay. Yeah, thanks.
You're welcome. I'll give you guys 2 more minutes or so, and then we will continue. All right, I hope everybody managed. Yeah, so I can show you real quick what I had in mind for the solution. It's very similar to what you see in the cell above, but what we want to do is extract from the array that contains all our data. We want to extract all the bands because we are going to get the color of the pixel. And then we are interested in row 18164, column row 2, 3, 4, like that. And then for plotting it, we can use the exact same as what's right here. I'm a bit lazy in copy pasting. But then we are going to plot the smoke pixel. Let's hope it's gray. It is. Okay, I hope everybody managed to get this result. The solutions are also stored in the solutions notebook. So if you want to look at that later, then you can do that as well. Yeah, almost done with the raster data. One more thing that I would like to show you guys is that you can also use Rasterio to create new raster files. And then again, you would use the Rasterio open functionality, but this time you would use writing mode instead of reading. I've added an example here, but first you can think, why would you want to do this? Well, again, because rasters often come with many different bands or a lot more information than you actually need. So to be sure that you don't use too much memory or make it a bit easier, you can, for instance, extract one band and then save this as a new data set. So this is an example how you would do that for only the green band, for instance. Yeah, it's always important to, in the end, close your data set, as we said in the beginning, because you want to release your memory resources again. So you can do that by calling the close method, and you can check if it's really closed this way. I've added quite some extra sections here that go into a bit more detail and are a bit more technical. There are also some assignments that you can do if you're interested in this topic, and all the solutions, all these assignments are also in the solutions notebook. But now let's continue to vector data. And then I think Margot would like to share her screen.
Yes.
Stop share.
I think you can see my screen now. Yeah, so as we just finished the raster data, we can dive into our into our second section, and that is the vector data. So going back to the example where I already gave you, I added a point and a line, but on the left we have raster data, and then we have vector data, and we can see that the cells that the raster data consists of cells and vector data consists of objects, which we also call geometries. And there are three main types of geometries, and these are points, lines, and polygons. And as raster data has one value for each pixel, vector data can have multiple attributes for each object or geometry. So for example, if this would be a land cover map, we could say this part is agriculture, and agriculture has an ID of 0 and an area of 10,000 hectares, and 1,000 people live there. Also, we can do this for the polygons, so the big areas, but also for points such as a house or lines such as a road. There are also many different types of vector data formats. Maybe you recognize the GPS exchange, which often is with hiking apps if you like being outdoors. But today we will work with GeoJSON, and this is because it's a very easily accessible and often used file. And GeoJSON is often stored as a text file in a JSON type format. And it simply consists of your different objects in your image. So here, as an example, I drew a point, a line, and a polygon. And these are called, in a GeoJSON, they are called features. So we see all the features here. Each feature has a geometry, so the coordinates. So the point has one X and one Y coordinate. And we can also see the type here. Now, I also linked all the libraries here in the PowerPoint, so you can look back at it later. But today we'll work with the two top ones as well. And these are geopandas and Shapely. And geopandas, as the name suggests, is the geodata version of pandas. So if I understand correctly, most of you at least have worked with pandas before. And geopandas also, just as pandas, works with data frames, but this time geodata frames. And this is typically a format of a geodata frame. So we have the regular data frame with an index and data, and now just one extra column where the geometries are stored. So these are the coordinates. And the second library that is often used is Shapely, and this is often used to create and manipulate shapes. So as you saw in the example, we have points, lines, and polygons. But if you want to have multiple points with the same attributes, but at slightly different locations, you can also create a multi-point or a multi-line or a multi-polygon. It's very straightforward naming. So now the question, of course, is how can we work with vector data in Python? And how can we apply this to our case study? So as Amber already mentioned, we want to use the land cover map. and extract the forest patches from our land cover map. So if this is our regular RGB image, we will, in the notebook, we will load a vector file, and you can recognize the shapes already. If you look closely here, you can see the legend. And you see that the light blue represents the forest. So you probably recognize the shape here, and brown represents artificial surfaces. So here's a road, and these small blobs are the city. So with this in mind, let's go to our notebook. So this is just the part 2 vector notebook. And also check again if you are in the right environment. Same as with the previous notebook, there's quite a lot of text which you can read back, and also there's an extra section. But I will just go over the cells and ask any questions you want, or read it back later. So, because we have these geometries, we are going to start by creating our own geometries to get a bit more feeling for it, and we can easily do this with Shapely. So with Shapely, we can import a point, a polygon, and line, and by providing the X and Y coordinates for each one, we can create the geometries. And as I mentioned, each object has attributes, and one of the attributes are the coordinates, so X, Y. And we can print these coordinates, and we see indeed that these match. So here you see first all the X coordinates and then all the Y coordinates. To see what we created, we can also use matplotlib to simply plot our geometries, and we see that we created a point, a line, and a polygon. Now, the X and Y coordinates aren't the only attributes a geometry has, and there are a few built-in attributes from Shapely which are quite useful. For example, you can check the geometry type, so for the point, line, and polygon. You can check the size or the area of a polygon, or the distance between two objects, in this case, 2 points. Also, I will go over this right now because it will take a bit too much time, but definitely try this out for yourself. You can just play around with this, try to replace this point by a polygon, see what happens. And to challenge you, you can also try to find the length of our line. Also, there are more inbuilt attributes which you can find in the Shapely user manual, which is linked in the notebook as well. So now what we came here for is, of course, working with real geographic data. So going back to our forest fire, we want to extract the forest from our land cover map. To do this, we need Matplotlib again for the file paths, and we need the geopandas. So this is the path in our data folder to our land cover map, and you can see it's a GeoJSON file. And we can load this simply with geopandas saying read file, and then just give file path. And by head, we print first rows. Where this is shown now. But we still see the data frame, and we can see that we have an index, as we expect. We have the data, and we have a geometry. As you can see here, we have the land cover class, which is either artificial surface, agricultural area, or forest and semi-natural area. And we also have subclasses. So in agricultural area, you have some parts are heterogeneous agricultural areas and some are arable land. Now, one of the main advantages also from geopandas is that it has a plot method. Which allows you to use a geodata frame, specify that you want to plot it, and say which column you want to plot. So in this case, we want to plot the land cover class and add a legend. So if we do this, we can recognize the plot from the object. Now, as an exercise, I'd like to challenge you to extract to create a new geodata frame with only the forest areas. So you're going to filter the data frame on the forest and semi-natural areas. And this is very similar to pandas. So I'll give you a few minutes, and then you can start. I'll give you 1 more minute, and then I'll show you the solution. Okay, let's continue. I hope you managed to do this, and otherwise, no worries. Of course, you can look back at it. It's a lot of information in one go. But the nice thing of geopandas, as I said, it's very similar to pandas. So if you have some experience there, will feel quite natural. So if we create a new data frame with forest df, we say then we want our forest data frame forest data frame, and now I'm gonna so use this. Sorry. For land cover class. So end of the word is forest and natural area. So if we do this, we can print our data frame again. And then we see we only have the data frame where land cover class is equals the forest area. And you might have seen the extra time hint. We can visualize this, and one of my favorite features from geopandas is actually the explorer method, and it's very similar to plot. So in plot we use the data frame for plot, and you say the column you want. Now we can say the data frame, so forest df explore, and for example now we want to show the subclass with the legend. And if we do this, you get an interactive map of our geodata frame on the right location. So here we can see the grid names. And if you hover your mouse over the areas, you can see all the attributes. So it's a really nice feature if you just quickly want to see what data you're working with. So to end, we want to write our vector data, just as we did with our raster data. We want to write it to a new file so we can take our hard work to the next notebook. And with one of the other packages, Fiona, you can check to which file extensions you can write. So here we see a bunch, but we don't need them all, of course, now. But we will use GeoJSON. So we specify a file path, and we can simply say that we want our forest data frame to file, and then we specify the file path and GeoJSON. So if we do that, you now have in your data file, in your data folder, you have the forest land cover GeoJSON. And there's some more information in the extra section as well for you to go over. But first, let's get back to a little bit more theory. Last part already. So now that we understand both vector and raster data, we can start combining it and working with real data. And as Amber showed, our visual data consisted of 3 bands, the red, green, and blue band. But this is only a very small part of the electromagnetic spectrum. And for our next exercise, we're actually going to expand the part where we're looking at. And we're also going to take into account the near-infrared region. And this is actually because by combining the near-infrared signal together with the red signal, we can create a new signal, which is called the normalized difference vegetation index, or I will call it the NDVI, otherwise this workshop will take a lot more time if I say it out loud every time. And the NDVI is actually an index to measure how green plants are or how healthy plants are. And it does this because it measures the greenness of plants, and this is actually the chlorophyll in plants, what make them green. And if a plant has a lot of chlorophyll, it usually absorbs blue and red light and reflects the green and near infrared light. However, if leaves die, for example, in autumn, you see it outside now as well, they slowly turn red. That's because there's less chlorophyll in the plant and it doesn't absorb the red light anymore. So that's why it seems red to us. And it also doesn't reflect the green light as well. So using this different NDVI, we can see where in our image the plants are healthy. So as you can imagine, after wildfire, there won't be that many healthy plants, unfortunately. So we're gonna go back to our notebook already. And here we see just the regular raster data. So from an RGB image before and after the fire, and this would be quite hard to see where the fire was the most severe. But by using the NDVI and the areas we extracted for our forest, we can see where the vegetation was the most damaged, and maybe also to see what type of vegetation was damaged the most. So let's go back to our notebooks and start on the final part. And again, check if you are in the right environment. So here's a short explanation then about the notebook, and we're just going to start immediately by importing the required library. So we already saw these in the past two notebooks. So we need all the libraries for both the rasters and vector data. And we're going to start by exploring the data. We'll
edit.
Sorry, I will clear my
Yes. And one below clears them all. Yeah.
Yes, at least you can see what. So loading the data, and then we're gonna take the RGB and near infrared rasters from our data folder with before and after, and we're gonna load them again with rasterio. Now, if we print the metadata, we can also see the summary of one of the rasters, and we already can see that the count now is 4 instead of 3, signifying that we have an extra band, so our near infrared band. And as I said, because the NDVI consists of both the near infrared and the red band, we can plot them before and after to get a feel for what we might expect. So here I use the show function from rasterio again with the red band, which is number 1, and the near infrared band. And that's the loading. Yeah, so I thought this is very nice to see already. But this gives us a first impression, because here on the left you see the before the fire images, and on the right the after, and you see that the red band doesn't change that much, but the near infrared does, and especially in the area where there's a forest, the near infrared significantly decreases. And looking at the formula for NDVI, you can see that as the near infrared decreases, the NDVI will decrease as well. So with this formula, we can also write a function to compute the NDVI. To do this, we need 3 things. So we need a raster image, so the rasterio image. We need to specify which band is the red band. So now it's every time it's 1. And we need to specify which band is the near infrared band. So this was the 4 band. First, I wrote a check if you don't accidentally use a visual image. So it needs to have 4 bands. And then we can simply read with the rasterio read function the red band, the near infrared band, and then we can apply the formula. If we do this, we can immediately create a raster or NumPy array for the before fire and after the fire. So because we do this division, we actually get a NumPy array instead of a raster. So we have to use the matplotlib imshow function. And we can see that we get an image of the NDVI, but we lost the coordinates around on the axis. So we need to save this again as a raster. And this is actually a bit more complex. As Amr mentioned, we need a projection and a transform. And you can read more about this if you're interested in the first notebook, but I will just quickly go over it, that we, as an input now, we need the data set, so the NumPy array and a path where we want to save it, and the other variables we can retrieve from the original raster image. So we do this with rasterio open and we put it in the right mode. So that was our function, and now we can apply this to our raster. So we want to write one raster for the NDVI before and one for the NDVI after. So if we now plot our images again, our coordinates will reappear on the axis, and we can actually start to compare the NDVI. And here again, you already see that this is much greener before than after. So now, where it all comes together, we are going to combine our vector and raster data, because looking at these images, it's quite hard to see by eye where the impact was the most here. So we're going to start by loading our vector data. So this is the forest land cover you extracted from the land cover map, and we actually going to plot the boundaries of the forest over our NDVI images. We also plotted here. This already makes it a lot more clear that why there are these distinct boundaries between the bright green and the yellow reddish colors. And also, if you compare this within the boundaries, it's much larger. To make this even more clear, we can also do a raster operation. It sounds maybe more fancier than this, but we are just going to extract the raster, subtract the rasters from each other to show where the difference is largest. So we are going to read the NDVI after minus the NDVI before and store this as a raster again. And if we read this raster, we can plot it. And this shows us where the NDVI has decreased the most. So this again corresponds to our forest area. Now, our next challenge is a bit more complex, but we want to see in which area the fire was most severe. So actually, we want to see in which polygon the decrease was the largest. So to do this, we need to combine it. So if we create a new geodata frame, we are actually going to add to this geodata frame two columns. One with the NDVI before as an average of the polygon for this row, and one with the NDVI after. So we can do this again with rasterio and shaping functions. And we're going to map the multi-polygons to a data type that the mask function can read. So it's a GeoJSON data type. And the mask function actually says, from this raster data, I will only want information that overlaps with the geometry from our vector data. And I don't want anything else, so we crop the outsides. And if we do this for every polygon, we can average that for each row. Define this function, and we apply this to each row in our data frame. And we get an average NDVI before and average NDVI after. So going to our next exercise, the challenge is to find out where, so for which forest polygon, the impact of the fire was most severe. So I'll give you 5 minutes again. And there are some hints in there.
Somebody posted on the chat. It's not a question, but maybe a bug or so. It says, did anyone else have a count of 1 instead of 4 for the before underscore fire underscore image file? Is it clear what they mean, or?
I think they have 1 band in their file for some reason, which should not be the case.
I don't know, but is this person certain it's not, he or she is not taking only the green band raster? Because that should only have 1 count.
Yeah, and could maybe be the way that they're counting or so. So if you want to explain more about the issue that you're having, you can type again in the chat or unmute yourself and speak up your so we can have more idea.
Yeah, I had the issue. I'm just seeing if I can drop a screenshot in the chat. But it's really just reading it directly from the file path and then just showing the metadata, and the count is 1 band instead of 4. And the file is NDVI before .tiff. That is the right file, right? Let me drop a screenshot.
I think you're reading the solution file. NDVI before .tiff. That should be 1 because that's only the NDVI.
Yeah. Yeah. Yeah.
Okay. So in workshop under data, I don't see a subfolder for solutions though. No, the file path
It's not in the solutions folder, but it's the NDVI files we created, the raster files for the NDVI. The only band that those have is the NDVI, because we only the NDVI is just one value. So actually, I can maybe show this. It will make this more clear.
Yeah, I get what you're saying, but oh.
So we save the raster here. We also say the data we save is band number 1. So all the NDVI files we store only have 1 band. Count 1. Okay, I hope you all managed, or at least made a start. Because of time, I will start showing the solution. So it's a 2-step solution. So first, we want to create an extra column in our geodata frame called difference NDVI, for example. And this is actually just a subtraction of the 2 columns. So average NDVI before minus NDVI after. So this will create a new column. And then we want to locate the row or the geometry where this is the largest. So in our geodata frame, we say we want the location of the wildfire impact column with the difference NDVI, where this is at a max. And if we then print this statement, we can see that this is our geometry with the largest difference. So the difference in NDVI is 0.08. And this is, of course, a forest. And the type of forest is crop and or herbaceous vegetation. So if you also want to visualize this, we can do as a last step. We can take the geometry of our row with the largest difference and plot this over our NDVI difference raster. So here again, we take the first band because the NDVI raster is only one band. And we can plot this over. So here now we know that this area was the most damaged. So possibly we can start here with replanting trees the soonest, or maybe see if the fire started there, or do further investigation for the future. So well done. You made it to the end of the notebooks. I hope you could follow a little bit. I'll close the raster and get it to you so as well, if you don't want your laptop to freeze. And I'll give the word back to Amber to close off.
All right. I'm sharing my screen again. Okay, so what have we learned today? First of all, geodata is a special type of data, as you know by now, because it's information that is tied to a specific location on the Earth. Geodata is very important because it enables precise mapping, analyses, and understanding of geographical features. And this altogether supports for informed decision-making. And this can be done in various fields, such as urban planning, disaster management, as we saw today, but also, environmental conservation, or many other fields as well. So that's probably the second bullet point. Yeah, informed decision-making. So today we looked at a use case of wildfires in Greece, and we saw that with the use of geospatial Python libraries, we could actually work with different types of geodata. Satellite imagery, which is stored as raster data, and land use information, which is stored as vector data. And this allowed us to analyze the impact that the fire had on our area. And this also enabled us to identify the forest patch that was affected the most by the wildfires. And these types of analyses can really aid in monitoring and in predicting wildfires to mitigate the impact of these types of disasters in the future. So that's really important. This use case was just one example of information that geodata can actually provide to gain insights in crucial solutions finding. So in finding crucial solutions for the major challenges that our world is actually facing today. So thank you very much for your attention and participation for today. We've added our contact details right here. Yeah. So please feel free to reach out if you have any other questions. And I think we will also have time for a discussion right now. So we'll give the word back to the PyLadies.
Yeah. Thank you so much for the presentation. I think it was really comprehensive and really interesting. And hopefully the others also thought the same. And If you have any questions, we have maybe time for 1 or 2 questions. So the stage is yours for questions.
I had a question, I guess a bit more about your workflows. So both of you showed libraries that can run data locally. But I'm wondering how much of your work is in the cloud, and do you use more distributed libraries and processes like Mosaic for vector data or for raster. I'm not sure what you might use. But like what's the split maybe about how much of work you do in the cloud versus more locally?
We do quite some data processing, and this happens all in the cloud, so you're right. But it's quite distributed as well. So we use different nodes that all take up their own tasks to compute the data. Most of our operations are actually raster operations, at least for soil moisture content. But from biomass, I think you also work more with vector data.
Yeah,
is that true?
It's mostly raster data, and sometimes for the fields, because we work at field level, we need vector data to say, okay, this is one field, for example. But everything we do is in the cloud. And for regarding packages, we also created a lot of our own packages to really do exactly what we want. But we rely on packages such as GDO. It's very important.
So thank you. And I also have a question. This is maybe more of an overview question, but where do you see the most difficulty that you have faced at your work working with geodata and Python that you can warn people against?
It's a good question. I think it really depends on your use case, of course. So some issues that we encounter are mostly related to the large amount of data that we need to process. So then memory issues, for instance, are something that we have to deal with. So then, as we mentioned before, you should really make sure that you are not keeping in memory way more data than you're actually using. So that's something that can become quite an issue. And sometimes we also use even a bit of Python. So that uses C functionality in Python to make some processes go faster if we need to do a lot of computations. So that's something that might be useful as well if you need to process a lot of data.
And I think if I look back when I started with geodata and my master's, just really try to often visualize what you're working with. That's one of the main advantages also for geodata, that you kind of can get a feeling for data because you can plot it on a map and it tells you something. And I've often worked accidentally in the wrong coordinate reference system, for example, and then it doesn't make sense at all.
Right.
So just check the data.
Yeah, so using QGIS or those kind of GIS softwares can always be very useful during intermediate steps. It's a good point.
Oh, we have one more question from Catalina. How do you compare this visualization to leaflet in Python?
Sorry, how do we what?
How you compare this visualization to leaflet in Python?
And then what do you mean with this visualization?
I'm not sure. Maybe Catalina can explain a bit more or unmute and ask a question, but that was the exact question I was reading out.
You mean compared to
Hello.
flow functionality?
I mean as a tool and also for computational.
Okay, I know leaflet, but I don't really have experience with working with it because we don't really use it here so much. I don't. Did you use leaflet before?
No, I never used it.
Okay, so it's JavaScript based, right? So you mean, or
Yes, it's for JavaScript, but also you can use it in Python.
Okay. Well, good question. I haven't used it before, so I don't know exactly.
I think it might
differences would
be
be.
interesting if you work more with applications where people want to see the data or move the data or have it interactively, but we really deliver a product such as an image, where it's a bit less relevant.
Yeah, leaflets more for interactive
Yeah.
maps, right? Yeah, yeah.
Yeah, I think that was all the questions.
I have a question. We have some time.
Yeah, me too.
Yeah, go for it, go for it.
Oh.
Maybe 2 questions and then we.
I will wait for mine because mine is based on curiosity.
Oh, well, mine too. So no,
Ah,
please
Then
go
go
ahead.
for it.
Serious people.
Then I take it. So is and maybe more following the next steps or more in depth. I don't think you mentioned it, but you can do something with deep learning, right? So to identify, right? Do you do anything at all, or maybe just more advanced level or different? Right? We were now working with just opening the images, combining the layers.
Yeah. Yeah, if you know how to work with raster data in Python, for instance, then you can start with machine learning also, of course. So you have many different types of algorithms that specialize in detecting certain objects or detecting changes or those kind of things. There's a whole world out there with Python libraries that are very suitable for those applications as well, like PyTorch or Torch Vision is a different one, I think. At Planet, there are also teams who focus on this as well. We are both not in such a team, but there are teams that focus on, I think, building detection. What is else? Forest car.
Yeah, also carbon
roads.
mapping and roads, but I think also an important part is that they use different algorithms to filter out clouds, for example.
Oh yeah,
That's
that's a good one. Yeah,
pretty
cool.
difficult thing of satellite images, but there are clouds sometimes. So yes, there's definitely a lot of interesting topics, and I think the main reason our teams are doing it because we want quite a global image, and it's very computationally expensive, but also you need to train it then on every area. So it's a trade-off there.
Yeah, maybe it's overkill, but maybe in a follow-up lesson session in the future.
Yeah,
That will be cool. Yeah.
Yeah. Thank you.
Thank you.
And I had also a question. Let me ask quickly. Thanks. So thank you for the workshop, of course, first. And also, I was wondering, mainly because I never work with notebooks. I wonder, in your own work, is it are they usually an exploratory stage, and then you turn the let's say the analysis that you have already written into applications that get deployed and run on images captured live and that kind of thing? So maybe if you could say a bit about that, that'd be nice.
I think I'm a bit more on the research side. But usually we don't really work with notebooks. This was mostly for the workshop now. But sometimes if there's a customer and we want to demo some data, then we can work with notebooks, but usually we just work in the editor directly.
In my team, we actually do work with notebooks. So there's some difference. No, okay, but it's different in every team, I think. But we usually work with notebooks when we try to research a new feature, for instance, for our product. Then in our team, we just do some experiments and we show each other using some notebooks. And then you're right, when you actually bring the code to production, we don't really use any notebooks anymore, because that's not really useful, of course. But yeah. So
but
different
you still
that's
use
the answer.
but you still use similar tools than Python and these similar libraries for the production work, I'm guessing.
Yes, yeah, so similar, yeah. So we have also built our own code or our own functionality to do similar things. And as Margot said, then it's a bit more optimizing what we want exactly, but under the hood, I think it uses a lot of similar libraries as well, like GDAL, for instance.
Thank you.
Thank you so much. We have two quick announcements about the next upcoming events. In November, on 28th November, which is the Tuesday, we have the next event, which is Privacy-Aware Machine Learning and Data Science by Catherine Jarpel. And it is in person in a central location in Amsterdam. And Catherine is one of the very initial co-founders of PyLadies in the global picture. So we're really excited for that event. It's in collaboration with Kickstart AI in Amsterdam Central. So that's lined up next. And after that, for December, on 9th December, which is a Saturday, we have a Python open source contributions day that is being hosted by Picnic. So for 2023, this is what we have lined up, and a lot of interesting events being planned for 2024 as well. So stay tuned. Hope to see you at one of the next events. And again, I would like to thank our speakers so much for hosting a really wonderful workshop, and to all of you for attending all the way here. In the interest of time, I'm not going to take the last question that just came up on the chat, but you can probably contact the speakers later, or maybe once I end the stream, we can still continue with the question. And thank you so much for joining. Have a wonderful evening.